Students, from today onwards, we will move to the Unit 3. Okay. So, Unit 3, the first chapter is flow measurement in pipes. Okay. So, this is the syllabus. So, this Unit 3 contains two parts. First part is flow measurement in pipes. And the second part is flow over notches and weirs. Okay. So in this class, we will start the flow measurement in pipes. So in this syllabus, in this chapter, first of all, we will discuss about the Bernoullis equation applications. Okay. So practical applications of the Bernoullis equation. Okay. So as we already discussed in second unit, there are some instrument is available based on its working based on the Bernoullis theorem. So Ventimeter, orifice meter, pitot tube. So these three instruments are very much important. It's working on the principle of Bernoullis theorem. Okay, this Ventimeter and orifice meter both are used to find the rate of flow. What is the other name of rate of flow? It is nothing but discharge. Okay, in a pipe. The pitot tube, it is an instrument that used to find the velocity in a pipe, in a closed conduit pipe. Okay. So next, momentum principle. Next, important, force exerted by fluid flow on a pipe bend. Okay. So this chapter is very much important. Why I am telling this very much important means, so this chapter is practically oriented. So in your laboratory, next semester you have laboratory, fluid mechanics laboratory. In that laboratory, we will do experiments in this Ventimeter, orifice meter. Okay. So please concentrate in this two chapter. So this third unit is very, very simple unit and easy unit also. We can easily to understand also. Okay. So flow measurement in pipes. First we will recall the Bernoullis equation. So Bernoullis principle states that for a perfect incompressible liquid, for example water, okay, flowing in a continuous stream, consider it is as a pipe. The total energy, that means the summation of pressure energy, kinetic energy and potential energy of a particle remains the same. Same means constant, while the particles moves from one point to another point. Okay, so the summation of pressure, kinetic, potential, okay, or datum head, pressure head, kinetic head, datum head. The summation of all this value is always constant in a closed conduit section. Say it is as pipe. Okay, at points along a horizontal streamline, higher pressure regions have lower fluid speed and the lower pressure regions have higher fluid speed. So what is that meaning? Suppose a pipe cross section is there, say it is the diameter is 100 mm, okay, 10 centimeter. Okay, so same pipe at some distance the diameter is reduced, say 5 centimeter. So now the liquid is flowing in that pipe. First initially it will flow 100 centimeter pipe. Okay, so in this the fluid velocity is very much less. Okay, so but the pressure is maximum. So higher pressure regions have lower fluid speed. Okay, so the same fluid is travel in the smaller diameter pipe. That means 5 centimeter diameter pipe. Okay, now what happened? Automatically the velocity get increased. So we already know if diameter decreases means velocity get increased. Okay, so due to this increasing velocity, okay, the pressure will be low. So the lower pressure regions have higher fluid speed. Here I mentioned speed is nothing but I am telling about velocity. Okay, so the Bernoullis theorem is also the law of conservation of energy. That is the sum of all energy in a steady, streamlined, incompressible flow. So steady, streamlined, incompressible flow of a fluid is always constant, not equal to 0. So we get some value. Okay, it is always constant in the entire length of the pipe. So this is the Bernoullis equation. So next, practical applications of the Bernoullis equation. So based on the Bernoullis equation, some of the instruments are derived. Okay, equipments are designed for our practical measuring purpose, measuring of the fluids. Okay, so Bernoullis equation is applied in all problems of incompressible fluid. So the best example for the incompressible fluid is water. Okay, incompressible fluid flow where energy considerations are involved, but we shall consider its application to the following measuring device. So there are a lot of instrument is there. As per this 3 is very much important. So as per your syllabus, this 3 only is very much important. So first one is Venturimeter, second one is orifice meter, and the third one pitot tube. Okay, so these 3 instruments are very, very important. So in this chapter, in this class, we will discuss now Venturimeter. What is meant by Venturi and what is meant by Venturimeter? So how to calculate the discharge. So like that we will see. So next class we will see the orifice meter. Okay, we will see one by one. So what is meant by Venturi effect? Venturi effect. So listen, students, kindly see this picture. So there will be a larger diameter pipe is there. So this diameter of the pipe is reduced after some length. Again it is increases after some distance. Okay, so here velocity in this portion velocity is less but pressure is high. Here low speed means lower velocity. Okay, so same fluid is traveled in this smaller diameter pipe. This is very, very smaller diameter. Okay, here speed is high but pressure is low. Okay, speed is high but pressure is low. So this is the fundamental concept. This concept is called Venturi effect. Okay, so sometimes they will ask 2 mark or 3 mark questions. What is the Venturi effect? So when your fluid moving through a pipe, faces a constriction of or narrowing of the pipe. Narrowing means the diameter, the cross section area get decreased. Okay, the velocity of flow increases at the section. Okay, with a corresponding drop. Drop means will get lower. Okay, drop in the static pressure. This principle is called Venturi effect. Okay. So Venturimeter. Let us see in this class Venturimeter. What is by Venturimeter? So this Venturimeter is working based on the Venturi effect only. Okay. So it is an instrument. It is an instrument which is used to measure the rate of discharge in a pipeline and is often fixed permanently at different sections of the pipeline to measure the discharge. So using this Venturimeter, so this is one attachment. It is like a small element only. It is an attachment. We have to attach in the pipe at anywhere. Okay. So from this we can measure the discharge. How much water is flowing in that pipe. Okay. So using the simple calculation we can easily form. So the principle of Venturimeter was demonstrated by Italian physicist G.B. Venturi. G.B. Venturi in 1797. So they dealt this Venturi effect in 1797. So at the time it is in only in book, that means theory only. Okay, in theoretical part only they studied, but it was first applied by C. Herschel in 1887. Okay, so nearly after 90 years only it come into the practical application. Okay, to develop the device for measuring the discharge. So Venturimeter, when it is derived at 1887. Okay, discharge or rate of flow of fluid through pipes. Okay, so the basic principle is that by reducing the cross-sectional area of the flow passage, a pressure difference is created. Okay, so we are reducing the cross section of the pipe. Okay, so there will be a pressure difference is there. Okay, and the measurement of the pressure difference enables the determination of the discharge through the pipe. So using the pressure difference, pressure drop is occur, using that we can easily find the discharge through the pipe. So this is the fundamental concept of the Venturi meter. So what are the components of the Venturi meter? There are three important components are there. Three important components. We will see one by one. Okay. So an inlet section followed by a convergent cone. So the first one is convergent cone. Second one is cylindrical throat. And third one is divergent cone. So there are three parts: convergent cone, throat, divergent cone. So let us see in the picture. We can easily understand. Okay, now you can see in this picture. So this is the pipe. This is the inlet pipe and this is the outlet pipe. See, water is moving from this direction. So you can see here a conical shape. Conical shape pipe is there. So this pipe is called a convergent cone. Converging cone or converging part. Okay. So what happened here? So the convergent cone at one end diameter is same as the pipe diameter. Okay. So it is keep on reducing. After some times, the diameter will get reduced. Okay, nearly half of the inlet pipe. So this is the 10 centimeter means this diameter is 5 centimeter. So after that, some distance, some length, throat. Okay, throat is the uniform cross section. So the convergent is the not uniform cross section. It is the tapered pipe, like a tapered pipe. But throat is the uniform section. So again, a divergent cone. A divergent cone is there. See, this length, this convergent cone length is less than the divergent cone length. So this divergent cone length is more. This is more. This is more length and this is less length. Okay, this is very less length. Okay, so throat is a small uniform cross section pipe. Okay, so now we are attaching manometer. So why we are attaching manometer here? To find the pressure difference. Okay, so now you can see here in this picture the manometer. This is a U-tube differential manometer. So in this, one end is attached in a pipe. That means inlet pipe. The other end is attached in the throat. Okay, one end attached. See, carefully listen. So many students, while in the examination, they wrongly draw this diagram. So some students, they draw like this in this divergent cone. Okay, they draw the U-tube limb at in the divergent cone. It is wrong. So one of the limb should be attached in a inlet pipe. So other end is attached in the throat. Okay, so this is inlet section, convergent, throat, divergent section and exit, outlet. Okay, and this is the manometer. This is the manometer, and this is the some data line, imaginary line. It is called data line. Okay, so this is the cross section of the Venturi meter. Okay, so this experiments we will do next semester in the fluid mechanics lab. So salient features of the Venturi meter. So the inlet section, first we will take inlet section. Inlet section of the Venturi meter is of same diameter as that of the pipe, followed by a convergent cone. Okay, followed by a convergent cone. So after inlet section, convergent cone. The convergent cone is a short pipe. That tapers from the original size of that of throat of the Venturi. Okay, so the convergent cone pipe is a tapered pipe having less length. Okay, it has an angle of 21 degree plus or minus 1 degree. So it is like a tapered, the tapered angle. Okay, tapered angle is 21 degree plus or minus 1 degree. And approximate length is 2.7 d minus d. Okay, 2.7 d minus d, parallel to the axis, where d, capital D, is the diameter of the inlet section. Capital D is the diameter. See, what is the diameter of the inlet section means? So initially water is flowing from the inlet pipe only. That means diameter of the inlet pipe. Okay, and small d is the diameter of the throat. So diameter, compared to diameter of the inlet pipe, diameter of the throat is very, very less. So suppose this is the diameter of the inlet pipe, means diameter of the throat is nearly half of this inlet pipe. Okay, half of the diameter of the inlet pipe. Okay, the throat of the Venturi meter is a short parallel side tube having its cross-sectional area smaller than that of the pipe. Okay, so very much nearly half of that. Okay, so next come to divergent cone. So the divergent cone is a gradually diverging pipe with its cross-sectional area increasing from that of the throat. Okay, so from the throat the cross-section increases to the original shape of the pipe. The total included angle in this cone is preferably between only 5 degree to 8 degree. So actually convergent cone angle is 21 degree, but see here divergent is only 5 to 8 degree only. Okay, and also the length of the cone is 7.5 times the d. Okay, so for that only I told previously the convergent cone length is very, very small. Okay, divergent cone length is very much big compared to convergent cone, such that the length of convergent cone to be smaller than the divergent cone. Okay, that also cone only. Okay, so convergent is very less length, divergent is greater length. Okay, so during diagram, when you draw the diagram in the examination, please keep it in your mind. Why I am telling? Because of some students are draw like convergent cone is length will be more, and convergent cone length will be very much big, and divergent cone length is very much small. Okay, so be careful. Convergent cone length is small, divergent cone length is big. Okay, so the pressure measuring system such as manometer, so we are using manometer, is mounted to measure the pressure difference at the inlet section under the throat. Okay, so this is the salient features of the Venturi meter. Okay, so now here you can see here some of the practical Venturi meter. Okay, so this is the industrial Venturi meter. See the size. So here you can see this is the convergent cone, and this portion is the throat T. Okay, and from here to here, see the length is the divergent. Okay, so water inlet is this end. Okay, say water is flowing from this end, moving from this end to this end and delivering from this end. Okay, so first initially water will move convergent and it will travel to divergent. Finally, it will outlet delivered to divergent. Okay, so this is the one of the industrial Venturi-meter. Okay, so next, here you can see a smaller. Okay, suppose the diameter is only 20 mm pipe means we can use this. So what is this hole? What is this hole means? So this hole is used to connect the manometer. You can see here, this is the convergent part. This is convergent. Okay, this is convergent and this is throat and this is divergent. Okay, and this is the inlet of the fluid and this is the outlet. Okay, so these two holes are used to measure the used to connect the manometer to measuring the pressure. Okay, pressure drop. So next, here also you can see here. I think this picture is very clear. So you can see here. See, this is the original diameter of the pipe. Original diameter of the pipe, and this part is the convergent, and this is throat, and this is divergent. Okay, this is divergent. You can see here, convergent length is angle is more. See this angle. This is 21 degree approximately. Angle is more, but length is very, very small. But here you can see here, angle is only 5 degree to 8 degree. Angle is less. So due to this less angle, the length will be more. Okay, length will be more. So you can see here manometer. So instead of manometer, they are used pressure gauge. Okay, pressure gauge. This is the advanced instrument to measure the pressure. So at inlet pipe, so they are not fitted in the convergent cone. They are fitted in the inlet pipe. Okay, one end, and other end, other limb is fitted in the throat to measure the pressure difference. Okay, so from this picture we can easily understand. And this is also one of the Venturi, industrial Venturi meter. Okay. Student, next we will see the expression for rate of flow through Venturi meter. Okay. So what is this expression for rate of flow through the Venturi meter? So what is our ultimate aim? To find the discharge, to find the rate of flow. Okay. So how much quantity of water is flowing in a pipe? Okay. So for that only we need some formula. Okay. So this is the derivation for that formula. I will explain step by step. Please follow my lecture. Okay. So now consider this is a Venturi meter is there. Okay. In this Venturi meter, this is the inlet pipe. So this is the convergent part, and this is the throat. Okay, and this is the divergent part. Okay, so inlet, convergent, throat, divergent, and this is the outlet. This is inlet and that is outlet. So the diameter is D1. Okay, this time inlet pipe diameter is D1. Okay, so consider a Venturi meter fitted in a horizontal pipe through which a fluid is flowing, say water. Assume the liquid is water, as shown in figure. Let D1 is the diameter of the inlet pipe. P1, pressure at the section 1. So at section 1, see here, section 1 is, it is the junction between the inlet pipe and the convergent cone. Okay, exactly here. Okay, V1 is the velocity of fluid at section 1. So velocity here. Next, A is equal to area of the section, pi by 4 into D1 square. Okay, see, this all the properties are inlet pipe properties, not convergent or throat. Okay, next D2, P2, V2, A2. So like this, D1, P1, V1, A1. Okay, are the corresponding values at section 2. So here you can see what is section 2. Section 2 is nothing but the throat section. Okay, so D2 is the throat diameter, P2 is the pressure in the throat, V2 is the velocity in the throat, and A2 is the area of the throat. Okay, so now I am applying Bernoullis equation. As I already told, this equipment is based on the Bernoullis theorem. So write down the Bernoullis equation. So P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. Okay. So as pipe is horizontal, so consider this is the datum line. So from the datum line, both the section height is same. Okay. So this also is Z1 and this also is Z2. Okay. So now write the equation. So both the section Z1 Z2 same, it get cancelled. Now write the balance thing. What is the balance thing in the equation? P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g. Okay, R. So this P2 by rho g comes to this side. This V1 square by 2g goes to this side. Now rewrite the equation. So here rho g, this rho g and here rho g both are common. Okay, so P1 minus P2 by rho g. This P2 will go to this side. So here plus is there, will go to this side means minus. So P1 minus P2 by rho g, which is equal to V2 square divided by 2g minus this plus V1 square by 2g come to this side means minus V1 square by 2g. Okay. So next, but P1 by rho g, P1 minus P2 by rho g. So this equation is the pressure difference. So P1, P2, what is this? This is the pressure. Okay. So P1 is the inlet pressure, P2 is the throat pressure. Okay. So is the pressure difference head. Okay, difference of pressure head because rho by g is there. Only P1 minus P2 is nothing but pressure difference. So denominator rho g is there. So it is the pressure head at section 1 and 2 and which is equal to H. So this I take as P1 minus P2 divided by rho g which is equal to H for simplification purpose. Okay. So substituting this value in the above equation. So H is equal to, in that above equation, H is equal to V2 square by 2g minus V1 square by 2g. Okay. So now applying continuity equation. So what is in the continuity equation? A1 V1 equal to A2 V2. Or so I need only V1. I need only velocity. So what happened? This A1 will come to this denominator. So A2 V2 divided by A1. Okay. So substitute V1 value in this equation. So here we know V2 square by 2g minus V1 square by 2g. So substitute V1 in this equation. So H is equal to V2 square by 2g minus A2 V2 divided by A1. So V1 is equal to A2 V2 divided by A1 square whole square divided by 2g. Okay. So simplify. So here 2g is there, here 2g is there, here V2 square is there, here also V2 square is there. So take it as a common outside of the bracket. So now what happened? This equation will come. So V2 square by 2g, take it as common. So 1 minus, what are the balance thing? A2 square divided by A1 square. A2 square divided by A1 square, which is equal to V2 square by 2g. So we take it as LCM. Finally we get A1 square minus A2 square divided by A1 square. Just to simplify. Okay. Take the LCM. Just to simplify. Okay. So now I need only V2. So what happened? H is equal to this value. H is equal to this value. So now I need only B2. So what happened? So keep it this B2 in the left hand side and all the terms goes to this side. The entire term goes to this side means what happened? B2 square equal to here 2G is there na? 2G into H. 2G into H. Okay, 2G into H. Here you can see 2G goes to this side. So 2G into H into A1 square. So this goes to numerator and A1 square minus B2 square goes to this side means it is come to denominator. So finally B2 square equal to 2GH A1 square divided by A1 square minus A2 square. So what is A2? So from this A2 is equal to here square is there. So square goes to this side means root. Okay. So take root. So root of 2GH into A1 square divided by A1 square minus A2 square, which is equal to, so A1 square root. What is meant by A1 square root? So it is A1 only. So divided by root of A1 square minus A2 square. Root of A1 square minus A2 square into root 2GH. This is the V2 formula. That means velocity at section of throat. Section 2. Okay. So all of you understand up to this. So first simplify this one. Pressure head equal to H. Okay. So H is equal to substitute H in this previous formula. So V2 square divided by 2G minus V1 square by 2G. So from this calculate V1. Okay. Using the continuity equation. So substitute continuity equation in this formula. Okay. So finally we get V2. Our ultimate aim up to this one is V2. Find out this V2. Okay. So we get A1 divided by root of A1 square minus 2G, A1 square minus A2 square into root 2GH. Okay. So now, what is the discharge formula? Discharge formula is Q is equal to A2 into B2. So what is our ultimate aim? To find the discharge. Okay. So here we know A2. So why we need to calculate B2? So we have A2. A2, how to calculate A2? Once we know the diameter of the throat, once you know the diameter of the throat, substitute the formula pi by 4 into d square, we can easily calculate throat area. But B2 only unknown. For that calculation of B2 only, we derive the equation. So B2 we already calculated. Substitute B2 here. So this is your A2. For V2 formula, we already found. This portion is the V2. Okay, A2 into V2. So finally, we got this answer. A1, A2. So this A1, here A1 is there, here A2 is there. So A1, A2 divided by root of A1 square minus A2 square into root 2GH. So this is called theoretical discharge. Q theoretical. Simply we can write Q T H E. Q theoretical. This is the theoretical formula. What is my theoretical formula? So we are calculating based on the formula. That formula we derive based on the theoretical condition only. Okay, so it is called a theoretical discharge. So another discharge is there. That is called actual discharge. Actual discharge. Okay. So the actual discharge is nothing but so based on the we have to multiply by the theoretical discharge into coefficient of the discharge of the venturimeter. So every venturimeter having some coefficient value. Okay. So CD is equal to actual formula of CD is equal to CD is nothing but coefficient of discharge equal to Q actual divided by Q theoretical. Q actual divided by Q theoretical. So we need Q actual means CD into Q theoretical. Okay. So here we return Q actual is equal to CD into. So this portion is Q theoretical. Okay. So CD value, how to calculate CD value? Okay, CD value is the coefficient of Venturi and its value is less than the 1. Okay, so once we calculate Q actual and Q theoretical. Okay, suppose water is flowing in the pipe. Okay, so actually you calculate the discharge. Okay, so collect the water in the outlet pipe for a particular time. Okay, how much velocity is flowing? Okay, that velocity into area of the pipe is nothing but the actual discharge. Q is equal to area into velocity is nothing but discharge. That is called actual discharge. Collect that one. Okay, so that is we can easily calculate. We need only stopwatch. Okay, so for a particular area, how much water is collected for a particular time. Suppose a container is there, so water is flowing in that container. Okay, for a particular height, how much time taken? So that is the multiply by the area of the container into that height of the container, height of flow divided by the time, h by t, area into h by t. H by t is nothing but the velocity. Okay, so area into velocity is nothing but Q actual. So these are all we will do in the laboratory. Okay, while doing laboratory we can easily understand. So Q actual, once you found Q actual, we can easily calculate CD value. So CD in the range of the 0.9. So the coefficient of discharge in the range of 0.95 to 0.98 for the Venturi meter. So always the CD value is less than 1. If you got CD value 1 or more than 1 means your calculation is wrong. Okay, so the actual discharge may be obtained by multiplying the theoretical discharge and coefficient of discharge. So Q, this is actual, Q actual. So CD value is equal to Q actual divided by Q theoretical. So I need only actual discharge. Our ultimate aim is what? To find the actual discharge only. So actual discharge means CD into Q actual. Okay, this is the formula. Okay, for calculating the discharge through Venturi meter. Okay, now student. So the value of the differential manometer. So how to check the differential manometer reading? So case 1, there are 3 important cases there. First, case 1, let the differential manometer contains a liquid which is heavier than the liquid flowing through a pipe. Okay, so let SH is the specific gravity of the heavier fluid. So here density heavier fluid we are using mercury. So SH is the density of the mercury and S0 is the specific gravity of the liquid flowing through the pipe. Take it as water. X is the difference of the heavier liquid column U2. That means mercury level difference. Suppose if you take this is the mercury tube. U2 differential mercury tube. So one end is connected in the inlet pipe, other end is, so this is inlet, other end is connected to the throat. So if pressure difference, okay, so this side, so this is the mercury level. So one end mercury level is lower, other end mercury level is higher. So this difference is nothing but the X. That means pressure mercury level difference. So finally the pressure head difference is nothing but using the formula X into SH divided by S0 minus 1. Okay. Next, case 2. If the differential manometer contains a liquid which is higher than the liquid flowing through a pipe. Okay. So suppose in a pipe having heavy liquid. Okay, having heavy liquid and manometer having lighter liquid. So under this condition, what is the formula? Suppose in a pipe is mercury is flowing. So in case 1, water is flowing. So now assume mercury is flowing. Okay. So in this U2 manometer, instead of mercury, water is there. That means lighter liquid. So under this case, what is the formula? So under this case, a smaller change in the formula. H is equal to X into 1 minus SL. SL is nothing but specific gravity of the lighter liquid divided by S naught. S naught is the specific gravity of the flowing through the pipe. X is same, difference in the head. Okay. So far we seen these two formula applicable for horizontal venturimeter. Okay. Horizontal pipe venturimeter. So in case of case 3 is inclined venturimeter. Suppose the pipe is inclined, means we have to use inclined venturimeter. Okay, so under this condition, what is the formula? The above two cases are given for a horizontal venturimeter. That means case 1 and case 2. This case is related to inclined venturimeter having differential due to manometer. Let the differential manometer contains heavier liquid. Okay, as in the first case. Okay, so under this, H is equal to P1 by rho G plus Z1 minus P2 by rho G plus Z2. So in this previous case, Z2 and Z1 will not come. Why? Means in horizontal venturimeter, from the datum, height is same. Height is same. Suppose in case of inclined pipe, height will not same. Datum height is different. So the inlet pipe height and the throat height will be difference in height because pipe is inclined. Okay. So under this condition, this is the formula. So H is equal to X into SH divided by S0 minus 1, and using this formula we can easily form. So similarly for inclined venturimeter, in which differential manometer contains a liquid which is lighter, as in our second case, in the liquid flowing through a pipe. So the value H is equal to P1 divided by rho G plus Z1 minus P2 by rho G plus Z2 is equal to X into 1 minus SL divided by S0, as in here. You can see here, same formula. Same formula, as in here. Okay. So this is the for this two formula for applicable for inclined venturimeter. So previous formula applicable for horizontal venturimeter. Okay. So this is the derivation form. Okay. Next class we will see the problems in the venturimeter. So problems are simple. Once you understand the concept and what is meant by conversion, what is meant by throat, what is meant by diversion, and formula. Okay, what is the Q actual formula? What is this CD? What is the CD formula? And what is the H formula? Pressure head difference. Mercury manometer reading, pressure head difference formula. Once you understand the formula, the problems are very easy. That we will see in the next class. Okay, now students. So once again, go through these formulas. Okay. So thank you, students. Thank you for your understand. We will meet in the next class. Okay. Thank you.